I'm going to have a really fun time with the second half of this video when we talk about the linearization theorem, because we get some cool results from a weird graph that's powerful and I love it. But anyway, we're going to start by talking about three types of equilibrium. We're going to have equilibrium that look like this blue one, where the functions are getting close to it. We're going to have equilibrium that look like this one, where the functions are moving away from it. And we're going to have a type that's neither. So these three types of equilibria are called sources. Sources, think of a spring, right? A spring is a source for water. Water is flowing away from that source of the spring. Okay, so it looks like this, where it's going away from it. So an example of a source would be y equals b here. It is kind of flowing away from that source. We have sinks. Think of a sink drain. Okay? Everything is going towards that value. All right? Just like over here, this equilibrium is an example of a sink because the functions are approaching that thing. They're all swirling down towards that sink drain. And the last thing has a bit of a weird name, and unfortunately it doesn't start with S. It's called nodes. Nodes are one of the other ones, which I know is not a very affectionate way to refer to them, but maybe it's going up in both directions or down in both directions. And I don't know if we've seen one of those yet in this section, but we will if we haven't already. Oh, we did. I just only showed one half of it. All right, that was the one that shoots off to infinity. It was actually a node for that equilibrium of y equals 1. All right, so let's use this a little bit, get some practice, do an example problem. Find and classify the equilibria for the following. That's not how you spell it. Equilibrium. And we'll do two examples. The first one's dy dt equals y squared plus y minus 6. And the second one is dw dt is some function g of w. Yes, I'm doing it to you again. Some function g of w, where here's w, and here's g of w. And we have some values at negative 0.5, at 1, at 2.5. And what g does is it goes down, and then it crosses, and then it bounces. All right, so I want you to pause the video. You knew I was going to say it. I want you to pause the video right now, find and classify all the equilibria for these two examples, and then we'll go through it together. All right, so we need to find, again, these are both autonomous differential equations. This does not depend on t. This does not depend on t. We need to find what values of y make this 0. And again, they both have unique solutions because they're both continuous with continuous derivatives as well. They are continuously differentiable. All right, so to do that, we are going to factor. When we factor, we're going to get y plus 3, y minus 2 right here. We're going to get equilibrium at y equals negative 3 and positive 2. We're curious whether these are sources, sinks, or nodes. We're going to create our phase line at y equals negative 3, y equals positive 2. And we're going to figure out what directions things are. And again, because we have continuity is very important for this. Because we have continuity of the derivative, we can use the intermediate value theorem, which says that if something is positive at one point in this interval, it'll be positive at all points in that interval. So we just do test points, just like the first derivative test. So if y equals 0, for example, what is the sign of the derivative? Well, if y equals 0, the derivative is negative 6. If y equals 0, we're decreasing. If y is negative 5, negative times a negative is a positive. Increasing. Positive derivative means y is increasing. If y is positive 5, positive, positive, positive. Derivative positive, function's increasing. So we can see that y equals 2 is a source. Things are flowing away, flowing from the y equals 2. Y equals -3 is a sink. Things are going towards it. Ooh, I don't know what this button does on my thing. Interesting. I'll experiment with that later. All right, we've answered the question. All right, let's just box the whole thing. We'll include the phase line. And we can do the same thing for this other one. Let's make our phase line. All right, we have 3 equilibria. When W equals -0.5, when W equals 1, and when W equals 2.5. This is also a continuous, W also has a continuous derivative. We can see the derivative with respect to W anyway. Over here we have existence, we have uniqueness, we have intermediate value theorem. And specifically, when W is really, really small, G is the derivative of W. G is a positive number. Again, don't look at the slope of G. The slope of G doesn't matter. G tells you whether W is increasing or decreasing. So W is increasing right here. And then it's decreasing in here. It's increasing here. And it's also increasing to the right of 2.5. Again, W is increasing. I don't care whether G is increasing. W is increasing because G is positive. So we actually have a node up here, and a source, and a sink. All right. Again, these graphs are tricky because we're not looking at the function itself. We're trying to figure out when is the function increasing and decreasing. We do that by looking at the derivative. The derivative is positive or negative based on whether G is positive or negative, which we can read from the graph. So pretty easy to get a little flipped around there. All right, let's end by talking about a fun theorem, and we'll use it in probably in the next video. I don't actually know whether I want to use it in the next video or not, but we're going to look at the linearization theorem. It's a pretty cool theorem, and it's going to look essentially at letter B that we were doing before. What this theorem says is it says suppose that y0 is an equilibrium point of the ODE that we've kind of just been working with, autonomous differential equation dy dt equals f of y. And specifically, I'm going to tell you that f is continuously differentiable. Again, that gives us existence and uniqueness. And then we're going to have something that should remind you of your second derivative test, actually, from calculus. If f prime of y0 is negative, we have something. If f prime of y0 is positive, we have something. And if f prime is equal to 0, something else happens. So leave some blank space. I haven't told you what's happening yet, because we're going to talk about it. All right? And remember, f is not the derivative of y. Well, f is the derivative of y, but f prime is not the derivative. F prime is the derivative of y, which is like the second derivative, which is why it's like the second derivative test. So let's look at what these situations talk about. We're going to classify, right? Y0 is an equilibrium point. We're going to classify whether it's a source or a sink. And what we're going to do is, it's called linearization because we're essentially going to look at something really close to y0. Here we're going to graph y and f of y. And if we're looking really, really close to this equilibrium point, this is y0, if f prime of y, so the derivative of the f, which is already a derivative, if f prime of y is negative, we're crossing like this. Now, I don't know exactly how we're crossing. We're looking at kind of a linear approximation near y0. And if f prime is negative, and again, let's collect all the information for why this picture makes sense. f prime is negative, meaning f is decreasing, and y naught is an equilibrium point, which means that f, the derivative of y, is equal to 0. Okay, that's why the picture looks like this. Well, is this a source or a sink? Well, f is positive below y naught. It's positive below y naught. And f is negative above y naught. Oh, this must say that y naught is a sink. Let me check my notes to make sure I'm not lying to you. I'm not lying to you. Yo, sink. No, y naught is a sink. All right. And similarly, right, if we have positive, we have a very similar graph. I'm going to be a little lazy here. It's the same graph. It just looks like this. Right? So the derivative f, which is the derivative of y, is negative and then positive. This will be a source. And if it's 0, our graph actually becomes a lot more interesting. Right, if it's 0, I'll label this one, because again, this one's more interesting. Phew, got dog hair on my face. If it's 0, well, we don't really know what's happening, right? Maybe it's a node where it's positive and then positive. Or maybe it's a node that's negative and negative. Or maybe it's a source. Or maybe it's a sink. We don't know. Okay? We don't know. We need more information. All right? And if you're done with this video and you want dinner, you are not alone. Hattie is giving her support to you. And the video's done. You can eat dinner. She cannot, because it's nowhere close to her dinner time, even if she wants it to be. Hope you have a good rest of your day. We'll finish with one last example problem, introducing the modified logistic problem model, and we'll incorporate all the stuff we talked about with phase lines and equilibrium points. It's going to be a ton of fun. You won't want to miss it.